There are different types of solutions. A solution can be composed of any combination of phases. Phase means state of matter. So solids, liquids, gases. Here's a table from your textbook showing some different types of solutions. A gas dissolved in a gas in a liquid in a liquid, a solid in a liquid, a solid in a solid. You might say, well, how could you mix two solids and have them form a homogeneous mixture? Well, alloys, mixtures of metals, are homogeneous mixtures. You can't mix them at room temperature. You have to heat them up and mix them together. And then as they cool down, you have a homogeneous mixture. So things like brass and pewter, gold that is not pure gold, something like 24 karat gold or 18 karat gold, has other metals in it. You can even have gases dissolved in solids or liquids dissolved in solids. So there's any kind of combination possible.
What things other than water count as liquids? Because I know like most liquids have water in them, other things.
Right, so most things that we encounter as liquids have water as the solvent, right? And that is because water is by far the most common liquid on Earth. There are other things. Oil, many oils are liquids at room temperatures. Acetone, ethanol, a lot of the alcohols the smaller alcohols are liquids. It's just that we don't end up using those very much. The gasoline is a liquid. The gasoline that you put into your car is a solution. It is a homogeneous mixture of many things. Some of them are liquids, some of them may be solids. And it's not, gasoline is not all exactly the same, but it generally functions the same. Does that help? Any other questions? When we talk about an aqueous solution, we've used this word before. In an aqueous solution, water is the solvent. And we have that special word because water is, it's often called the universal solvent. It's just so many solutions are aqueous. You can't just take two things and mix them together and expect them to form a solution, even for water. So if you're looking at a particular solvent such as water, it's not going to dissolve everything. When we refer to solubility, we forget how to talk. Solubility is the amount of substance that will dissolve in a given amount of solvent. Often that's 100 grams or 100 milliliters of water. So how much sodium chloride will dissolve in 100 grams of water? That would be the solubility. For some substances, it's a large number. For some, it's a small number. That solubility depends on the tendency towards mixing that all things have, and also on the types of intermolecular forces. Here's just an illustration of club soda, which is carbonated water, basically. Carbon dioxide dissolved in water. So we see that many systems tend toward lower potential energy. We've talked about this. You watch the cartoons and they're moving a piano and they're it's hanging out the second story window, right? And the rope breaks. What happens to the piano? It falls. Why does it fall? Potential energy, actually. It's high potential energy, and when that rope breaks, it's going to fall because that lowers its potential energy. As it falls, the potential energy is converted into kinetic energy. Yeah, so kinetic energy was involved in that. When things mix, though, we can't explain this just in terms of potential energy. If we look at two gases here, neon and argon, in a container, again with a removable barrier. We've got pure neon on one side, pure argon on another side. We take the barrier out. We understand that those are going to mix together, right? Kinetic molecular theory of gases, we've learned that gas particles travel in straight lines until they bump into something, and then they have an elastic collision, and they change direction and keep going. And so these guys are zinging along. You remove that barrier, and they're going to get into each other's space, right? Does that lower the potential energy of those molecules, those atoms? No, it doesn't. So why do they mix if it doesn't lower their potential energy? There has to be some reason. So the reason is entropy. Entropy is a measure of energy randomization or energy dispersal in a system. Nature has a tendency to spread energy around. It doesn't have it concentrated. If it has the opportunity, the energy will spread out. So when two ideal gases mix, the kinetic energy of each gas becomes spread out or dispersed over a larger volume. And that is an increase in entropy. Entropy is always wanting to increase. So if we look at this diagram in here, so the neon atoms have some kinetic energy. The argon atoms have kinetic energy. But the kinetic energy of the argon atoms is confined to half of this container. We remove the barrier, and now the kinetic energy of the argon atoms can spread out over the entire container. And that is an increase in energy, increase in entropy. Too many E words. Entropy also explains transfer of thermal energy from hot objects to cold ones. We know that, like, if you take a cooler and you stick maybe hot banana bread and a thing of ice cream in there, right, and you close it up, what's going to happen when you come back a couple hours later? The ice cream will be melted. It'll probably leak out of the container and soak into the banana bread, and the banana bread won't be warm anymore. Why? Why did it do that? The thermal energy in the banana bread wants to spread out if it can. And so it spreads out and goes into the ice cream, and everything in there becomes the same temperature. And that's what entropy does. Entropy, you can also think of as a tendency to disorder. And my house is a display of entropy on a regular basis. So, get motivated on the weekend, you get all things cleaned up, everything's good, all the Legos are back in their boxes, etc. The dog hair's all vacuumed up. And, you go to work Monday morning, you come home, and there's Legos everywhere, and dirty dishes, and there's just these little mounds and tufts, drifts of white dog hair. What is up with that? It's life. Life is messy. It's entropy, really. Spreading things out. You think about a deck of cards. All nice and organized, all lined up, all facing the same direction, and you drop it on the floor, what happens? They go all over the place. Did you have to work at that? Did you have to make it do that? Nope. Because that's dispersing energy, it's making things more random. And nature has that tendency. The leaves on a tree have order, right? They're all attached at the same kind of end with their little stems, and they're on the branches, and they're all pretty. And then fall comes, and they change color, and they drop off the tree. And where do they go? Into a neat pile underneath, all lined up? No, they blow all over the place. That's entropy. So we've got that tendency towards mixing and the entropy helping to create solutions. We also have to consider intermolecular forces. Intermolecular forces may promote the formation of a solution, or they may prevent the formation of a solution. So here's a brief review of intermolecular forces. Between nonpolar molecules, we're only going to have dispersion forces. Between polar molecules, we can have dipole forces. If we have fluorine, oxygen, or nitrogen bonded to hydrogen in a polar molecule, we can have hydrogen bonding. And then if we have an ionic compound in a mixture with a polar compound, we can have these ion-dipole forces.
Where do ion-dipole forces fall in the scale of things?
That's a good question. Where do ion-dipole forces fall in terms of strength? I believe they are stronger than hydrogen bonding. That's a generalization. Yeah, ion dipole forces can only happen in a mixture because you can't have ionic charges and dipoles in the same molecule. It's not possible because they're two different. One's a molecular compound and one's an ionic compound. So when we look at a solution that's trying to form, there are two components, the solvent and the solute. So the solvent molecules are attracted to each other by some sort of intermolecular force. The solute molecules are attracted to each other by intermolecular forces. And there will also be some sort of attraction between the solvent and the solute molecules. Whether these will mix together and form a solution depends on the relative strengths of these forces. I wish there was a better way to present this. The solvent, solute, 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 solvent, solvent, there's just too many S words. So if the interactions between the solvent and the solute are stronger than the interactions of the solvent molecules with themselves and the solute molecules with themselves, we'll get a solution that will form. Right? It's way too much. If those interactions are approximately the same, a solution will form. If those interactions are less than the interactions, they're weaker, the solution may or may not form. It depends on how different it is.
So can we just say greater than or equal?
Can you say greater than or equal? For the most part, yeah. So I'm going to go back to this picture. Okay, so I'm going to do an analogy here. So the solvent molecules are Japanese people. My husband's Japanese, and so nobody can get offended about that. And the solute molecules are Swedish people, and I am of Swedish descent, so nobody can get upset about that either. Okay? Because if you make fun of your own ethnic group, it's okay, right?
So are your kids Japish or Sudanese?
I say they're half Viking, half samurai.
Ooh.
Nice.
So Bikerai?
No. They're Viking samurai. They're Viking samurai. That's an excellent question, though. Okay, so imagine you've got a big room with a bunch of people in it. Half the people are Swedish, they only speak Swedish. Half the people are Japanese, they only speak Japanese. Are these people going to mingle and mix thoroughly? No, what's going to happen? You're going to have separation. You're going to have at least clumps, right? You'll have small conversation groups of Japanese people speaking Japanese to each other and Swedish people speaking Swedish to each other. Why?
Because they understand each other.
Because they understand each other, right? It's so much easier to communicate with someone who speaks the same language, right? It's very difficult to communicate with someone who doesn't understand what you're saying, right? Charades can only go so far. So if the types of interactions between the solvent molecules are very different than the types of interactions between the solute molecules, then they won't be able to talk to each other. The interactions between solvent and solute are going to be very weak, and there's not going to be much mixing. Now, actually, most Japanese people also speak English, and most Swedish people also speak English. And so if we have the same group of people and we realize, oh, everybody speaks English, now they're going to mix it up nicely because they could talk to anybody, and so you'll get a lot of mixing occurring. Does that make sense? So if we have strong attractions between the two types of particles, they're going to mix up really well. Another way to think about this is, in order for these solute particles to mix into the solvent, let's think about maybe the solvent's a glass of water, so that it's not the glass, it's the water in the glass. The solvent's some water, and we're trying to put something in it and have it mix up. Well, the water molecules are attracted to each other with hydrogen bonding, right? They're like, oh, we like each other and we're just swimming around here and we're all happy and everything. And then you try to put some solute particles in here. For the solute particles to get into the water, they have to disrupt the interactions between the water molecules. They have to disrupt the hydrogen bonding. Well, that needs to be replaced with something. It needs to be replaced with interactions between that interloper, this person who's butting into this group. There must be some positive attractive forces between the solute and the solvent in order for that to happen. If these forces of attraction are very weak, it's not going to happen. Water's just going to exclude the solute. Any questions?
So, like between oil and water,
Mm-hmm.
when you pour the oil in the water is basically so excited about itself that it pushes the oil out.
Yes.
That's
When
why
you,
it comes out on top.
yep. So when you add water to oil, water is just so attracted to itself, it just excludes the oil. The reason the oil is floating on top is because of its density. There are other substances that are also nonpolar but more dense than water. And so when you try to mix them with water, you see the same sort of effect. If you shake it up, you'll see these little tiny globules of that liquid in there, but then when you let it settle out, the water will be on top and the other solvent will be on the bottom. But yeah, that's exactly what's happening. Okay, so we should be able to answer questions like this. Determine whether each compound is soluble in hexane. So the first thing is, what the heck is hexane? We learned how to name organic compounds, just the really basic ones. Hexane, hex means 6, right? So 6 carbons. And what are the other atoms in there? Hydrogen. So hexane is C6. So 1, 2, 3, 4, 5, 6. That's the sort of math you have to do in OChem. It's a lot of counting of things like that. And then there'll be hydrogens all over the place. Because each of those carbons needs 4 bonds, we know that they're all single bonds because of the suffix -ane in hexane. So there's no double bonds here, it's all single bonds. So that would be hexane. Is hexane polar or nonpolar? Nonpolar. We can look at this structure and say, oh, it's really symmetrical. I don't see any lone pairs anywhere. That would cause you to guess it's nonpolar. The other thing is, the one exception I told you about different elements forming polar bonds, I said for the most part, if you have 2 different elements like carbon and hydrogen, you would say that bond's polar, except I want you to remember the carbon-hydrogen bond is considered a nonpolar bond. So all of these bonds are nonpolar. So then even if it was lopsided, it would still be nonpolar. So our solvent is nonpolar. What sorts of forces do nonpolar things have? Dispersion forces. So when we try to identify if these will dissolve, if they are soluble in hexane, we're looking for, do they have the same types of interactions that the solvent does? So what about water?
Polar.
Water's polar.
Hydrogen bonding.
It's got hydrogen bonding, so it's got the really strong dipole forces.
Probably not.
So the water is not going to communicate well with the hexane. The attraction between these is only going to be the dispersion forces. The attraction between water molecules is hydrogen bonding, dipole forces, and dispersion forces. Water's pretty stuck on itself. It is not going to mix it up with hexane. Does that make sense? So this would be a no. No, not soluble. How about ammonia?
No. It's got hydrogen bonding.
I heard a no and a yes. Well,
Polar.
It's always a good idea to draw the Lewis structure.
It can't hook up to another hydrogen because hydrogen can only have one.
So there's a lone pair on the nitrogen, and these bonds, nitrogen-hydrogen bonds, are all polar, but really what we're concerned about, if there's a lone pair in the central atom, is polar. So this is also a polar substance. And does it have hydrogen bonding?
Yes.
Yeah, it does. So is this going to mix it with hexane? No.
Hydrogen bonding is to not.
Pardon me?
Hydrogen bonding is to not. Nitrogen, oxygen.
ET phone home. That's if you remember it different, that's fine. But
This one, no, I don't know why it works.
well, great. But then when you say it, I don't understand what you're saying. Yeah. Okay. How about propane? Is propane polar or nonpolar?
Non-polar.
Nonpolar. It's just all carbons and hydrogens. So this one's nonpolar. Will it mix with hexane?
Sure.
Sure it will. How about hydrogen chloride?
I can't.
You can't remember. Well, that's honest. Let's draw the Lewis structure. Okay, that's a diatomic molecule, 2 atoms. So if the bond is polar, the molecule's polar. Hydrogen and chloride are different. What's our best guess?
Polar.
Polar. And it is. So this is polar molecule. Will it mix well with hexane? No. Any questions? Yes.
When you destroy it, it would have a dipole-dipole.
It would have a dipole-dipole. So these two have, everything has dispersion forces. These two being polar have dipole-dipole forces, and they have hydrogen bonding. This one down here has dipole-dipole forces and dispersion forces, but it doesn't have hydrogen bonding. So would this mix with water? Yeah, it probably would, the hydrogen chloride.
Oh, yeah.
Yeah. So the general rule of thumb is like dissolves like. So if you have 2 polar things, they'll probably mix together. If you have 2 non-polar things, they'll probably mix together. That's a rule of thumb. It's not always true. Why a rule of thumb and not your pinky or your index finger? I don't know.
Sorry, there's one.
Maybe thumbs are more uniform in size. That's what Google's for, right? Maybe people are less likely to lose their thumbs.
That's part of one of my knobs.
No, I'm sure there's some reason. I think, yeah, somebody will Google it and we'll find out.